Host disabled share participant
wait,
share.
sir. Okay, now try, sir, please.
It is a green tab at the
Yes,
bottom.
I have done that.
Yes.
Sir, now see.
Now
And you can make
can
it
you see?
okay. Okay. Yes.
Okay, great. So when shall we start?
First of all, I will give you an introduction to the participant in 5 minutes, and then we will start the session. Okay. And for any question, participants will put their question in the chat box that you can see. Okay. So shall we admit all the participants?
Yes, you can
log in.
Yes.
Okay.
Yes.
So, just go admit.
Now that okay, now what is the chat box?
So it will take some 5 minutes.
Okay.
So that all the participants can enter the room.
And now sharing. What is the chat box?
Sir, chat box is a side of the share screen. Left side.
Okay. Yeah.
Okay.
Yes. Okay, I got it.
If you click on that, you see all the participant message.
I can see everything now. Things
Okay.
are fine.
Okay. Thank you, sir.
So we will wait for 2-3 minutes. At sharp 2 p.m. we will start the session. Okay.
Sure.
So,
so how many participants are there today?
it will be near about some. We have total 550 participants.
550 participants.
Yes.
Oh my God.
But near about 400 participants will log in.
Wow, that's a huge number.
Yes. And all participants are faculties. Some research scholars are there. Yes.
Okay, great. So
we received a good response for this FDP.
So very nice, very nice number. I thought it will be around 50, 60, 100.
No, it is a large number.
So how are you doing nowadays? Huh?
Yes, I'm fine. So I am at Nagpur now.
Yeah.
Yes.
So good. So that coronavirus, what's the scenario?
Yes. It is much affected the country. Actually, all the institutions are not working properly nowadays.
So do you have there in your institution, is it working or it's kind of not functional now?
We at our institute we are working from the home only.
Okay.
But now we are attending the institute at 10% attendance.
Okay.
So alternatively, we are going to the institute. सरांचा लॉग आउट झालाय का? शेखर सरांचा आहे ना? Oh. So shall we start now?
Yes, maybe we can start.
Okay. So I will give your introduction first, and then we will start.
Okay.
Okay. So good afternoon, one and all, and I welcome all the participants for this afternoon session. So for this afternoon session, we have Professor Dr. Shekhar Sarkar. Professor Shekhar Sarkar is working as the assistant professor in the discipline of civil engineering at IIT Indore. Professor Shekhar Sarkar has completed his postdoc from Texas A&M USA. He completed his PhD from the ISC Bangalore, and he completed his MTech from the IIT. Friends, the research interest of the Professor Shekhar Sarkar is the derivative-free formulation in mechanics, that is the computational and solid mechanics, and then multiple crack propagation and failure of the structures. And his research interest also includes the metastructure inverse problems of the solid mechanics theories. Professor Shekhar Sarkar is also having the research projects funded by the government, that is the government of India, under the DST, that is the Department of Science and Technology. Professor Shekhar Sarkar is having the SCRB project, that is the Science of Engineering and Research Board, and the project title is the Peridynamic like framework to predict failure of concrete structures. Also, the Professor Shekhar Sarkar is having the Spark project, namely the safeguarding the heritage structures using the seismic metamaterials. Professor Shekhar Sarkar has published the papers in very renowned journals. A few of them are the Physicality Nonlinear Phenomenon Journal, then the Journal of Mechanics and Physics of the Solids. Professor Shekhar Sarkar has already published some papers in the journals, namely the Physics Letters also. So he has a good publication records, and he is working in the area of this computational mechanics. So on behalf of the Department of Civil Engineering, Government College of Engineering, Karad, and Department of Applied Mechanics, Government College of Engineering, Nagpur, we welcome you, sir, for this 5 days FDP. So this is the afternoon session of today's. So I welcome you again, and now I wish you to start the session. So please start the session. Okay.
Thank you, Professor Rajan, for introducing me to the audience. It's my pleasure to be able to deliver a talk to the faculty members and research scholars, I guess. Yeah. Yes, I have got some expertise in computational mechanics front. So I thought I'll be, maybe I'll discuss on that line itself.
Okay.
So what I thought is like, because I typically prefer this classroom type of teaching, like blackboard. I don't like electronic gadgets while teaching. So it's kind of a very new experience. Now we are getting used to that slowly because of this coronavirus thing.
Yes.
So what I'll do, what I thought is I'll go very slide by slide. I have, because computational mechanics, you will have basically a lot of equations, right? And some, because without that we cannot, it's not, we cannot just bullet a few lines and then talk about that. I believe that's not a very good way to learn like mechanics. So maybe I'll, and so that's why if anyone feels to ask anything at any point, please feel free to stop me and ask. Because if I go through slide by slide fast, I mean, once you lose it, I believe it will be difficult to catch again in this. So it will be better to stop, go slowly, and let's try to learn. I mean, of course, you will be all knowing computational mechanics. There is nothing new in it, but let's see. I'll try to look at it from a slightly different perspective. And Yes, I worked with Professor Jain Reddy actually. So maybe I'll
Sir,
try
please share your screen, sir. It is not
yeah,
visible.
yes, I'll share that.
Yes.
So I'm trying to share my screen. So let us see.
It is a green tab at the bottom side.
Yes, yes.
Yes, now it is
And
visible.
yes.
Yes.
So I'll try to start from the very basic. Okay.
Yes, sir.
And
Please
then
make it in the presentation view, sir. Please
yes,
enlarge it.
I'll do
That
that.
presentation mode.
Yes. Now is it fine?
Okay.
It's in a slide mode, I guess. Okay. So computational mechanics. It starts from, I think you can all see my slide. Yes. It starts from this picture, basically. It's a very common, you will find it any textbook, as a matter of fact. But this preserves the most important message of computational mechanics. So before we go ahead, I will first like to draw your attention to what mechanics is all about. See, there are three types of mechanics. One is quantum mechanics, then molecular mechanics or atomistic mechanics, and then comes computational mechanics. So three types of mechanics are there. Now, why do you need? Am I audible? I think. Am I audible to you, Dr. Rajan? Hello. Yeah, I'm audible, right?
Yes, yes.
Yes. So what I was saying is like we must appreciate upon the fact that where computational mechanics is slightly different from, let us say, atomistic mechanics or molecular dynamics. We have molecular dynamics codes and theory for a long time, right? And we have very fast computers. So why do we need continuum mechanics? As a matter of fact, we don't need that. We can solve any problem that we want using molecular dynamics. It can model very correctly failure of concrete structures. It can model everything almost. Now, where do we need that then? Now, the question is, when you actually go to solve any realistic problem of engineering interest using molecular dynamics, you will face the huge difficulty of scalability. What does that mean? Scalability means you cannot solve any engineering problem of relevance to us using molecular dynamics. Your computer will explode. The degree of freedom for solving, let us say, a small nanometer scale problem itself becomes quite challenging using molecular dynamics. So that's why, even though it has the potential to solve everything, it cannot, in reality, it cannot solve almost any problem of our interest. Now there comes the necessity of something that can be used to solve large scale problems, and that is called continuum mechanics or solid mechanics. Now we must have read this Timoshenko's book, right? Or we must have read this Euler-Bernoulli's beam theory and all that. But basically this concept of continuum mechanics started with the work of Euler, Bernoulli, Cauchy, these great people 200 years back. So basically what does it say? It says that solid is a continuum, means if I now try to see this, solid is a continuum means there is no gap on this body. Okay, actually, if you use a microscope, you will find that there are lots of atoms or molecules in it. Oh, I cannot. But one second. Why I am not able to? I'm sorry. Actually, I wanted to use my pen here. Anyway, maybe that's not possible. Okay, so this point is like this blue. Oh my God. Why I can't use my pen? Just a second, okay? I'm trying to use a pen. I thought of using online pen. No, anyway, that's probably not possible anyway. So the point is, like, you see at this blue body, this black is a representative point. Of its location is X. Now, under some deformation map, the sky is a deformation map that maps a point from R3 to R3. You can see that. What is R3? Is a R3 depicts this three-dimensional problem: X, Y, and Z axis, right? X axis, Y axis, and Z axis. And then and then at the after deformation, also the problem remains 3D. So that's talking about something very trivial. So it's mapping something in 3D to something in 3D. And continuum means there is no gap. So it's absolutely full. It's a continuum. So you can go to any arbitrarily close point to this point X, capital X. So that deformed point is small x and deformed point is capital X. Okay. Now, this is the basic point. Now, another important, very important assumption of continuum mechanics is, if you want to take a point close to this point X, you can see from this slide maybe that is X plus dx. And this dx can be arbitrarily small. Dx can be arbitrarily small. What does that mean? That means that you can like take go to any close as close as possible, but that is not possible in molecular dynamics, because molecular dynamics atoms are realistic and atoms are gaps. There are gaps between 2 points, but in continuum mechanics there is no gap between 2 points, and that is why you can take a very close point in the neighborhood of the point X. You can talk, this word is neighborhood, means you can just take a very small neighborhood of point, that is X plus delta X. Now after deformation, means you apply some load and this body deforms to some other shape. You can see on the right hand side, and thus the new point, the point X plus position initially was capital X plus small d capital X. It now becomes small x plus small d small x. Okay, so that exists in molecular dynamics. That does not exist. So it's basically trying to do some kind of homogenization, if you see from a different perspective. So what does that mean? It's basically a Taylor's expansion. You see at the bottom of this slide, small x plus small dx is equal to chi is the map, chi of capital X plus capital dx. You see this point, second point, that is x plus delta x, x plus dx. Now what is it that we are trying to do? You want to predict where does this point, neighborhood point, go after deformation. How are you deforming that? How are you getting that? We are trying to predict where will it go from point capital X. You see, so that is why we are trying to say chi capital X plus dou chi dou x dx. We are doing basically a Taylor's expansion, nothing else. We are doing a multidimensional Taylor's expansion. What is that multidimensional about? Because X can be 3-dimensional, X can be 2-dimensional, X can be unidimensional. So if you take this derivative, where dou chi dou x, that is nothing but f, that is deformation gradient. If you have read, I think you know that what deformation gradient means in continuum mechanics, right? So that if you expand, it's like a matrix. Dou chi 1 dou x1, dou chi 1 dou x2, dou chi 1 dou x3, like that. It's a 3x3 matrix that you get. Suddenly it becomes like, you see, it's a 3x3 matrix that you bring in, and that is called deformation gradient. All important. So what are we trying to do? If you now carefully see, small x plus small dx is equal to small x plus f d delta x. So the point is that you want to predict this x plus delta dx position after deformation. but not by using the information at small dx plus small dx. You are trying to use the information of capital X and its derivative. So basically, f is a derivative information at the point capital X. Okay, so you are using these two information, the position and its derivative of that position. That's all you are going to use, because continuum mechanics, what will it finally give you? It will finally give you some differential equation, right? Partial differential equation. So du dx plus 1 is equal to 0, something like that in some form. So, so that means it's a flow information. So you are not trying to actually go to the deformed position and measure its location. Rather, you want to predict from its information that you get at point X. Okay, I'm repeating this word because that is the most important aspect of solid mechanics. You want to try to find some flow information, that how deformation varies spatially, and you want to predict that from point X. Okay. Now to do that, we have defined what is small dx and what is small capital Dx. I'm going to be a bit mathematical in this slide because I think without this you lose the flavor of continuum mechanics. So what is ds? You think in a continuum, in a solid body, you can draw a line from any 2 points, right? Because that any 2 point exists. So I call this a fiber. That is ds fiber. And what's the length of that fiber? The length of the fiber is small dx dot small dx. So that gives the length of that infinitesimal fiber in the deformed configuration. And the same fiber in the undeformed configuration, its length was small dx, small d capital X. So the length was small d capital X dot small d capital X. Okay, in 1D it will be dx square, right? D small x square minus d capital X square. That gives you in 1D how much stretched a fiber has, how much the fiber has stretched, right? In 1D fiber, initially it was like this much. Then you apply some force and it expands or it contracts, right? It expands. How much it has expanded? It expanded like d small s squared minus d capital S squared, square root of that. Okay, why are you using square? Just to forget about mostly this, mostly the sign, plus minus and all that. And in time in 3D or in 2D, it's nothing but an inner product. In 3D, a fiber stands, right? What's the length of the fiber? Its position, initial position x1, y1, z1, and then here it's x2, y2, z2. Difference is x2 minus x1, y2 minus y1, or z2 minus z1, and norm of that. That's why I'm calling this dx dot d small x, right? And then d capital X dot d capital X is the initial length of the fiber. That's the minimum we are trying to information we are trying to use. And we have already understood that d small x can be written as f of d capital X. What is f? F is deformation gradient. Now this small x dot small x is small dx transpose dx, right? That is what that is how we write scalar, like transpose operation, we know. So that is how it becomes dx f transpose f dx. You see this derivation, did you understand? Like f d capital X dot f d capital X. Then it becomes, if you now simplify a bit, it becomes f transpose f minus I. Both sides is dx. So we are getting, and then this C, we are calling this f transpose f as C. These are all having great names like green tensor, Cauchy green tensor, like that. But I'm not going to that name for the time being. Then what is it? That so the stretch information you could write as ds square minus d capital S square is equal to 2 of dx dot e dx. What is E? E is the strain. You got E is equal to half of C minus I. How do you know it is strain? You are see because we are just trying to capture the length change to understand the strain of a fiber. That is the way to understand like in a 3D continuum mechanics. Now I'm calling this E as strain, but does it qualify to be something like strain? How do you know that? See, a fiber, I started with a fiber, right? Then I can pull this, I can take this fiber from here to there. That means I can rigidly transport a fiber from one point to another point. And if I do so, does the fiber get strained? No, it should not, right? I'm taking this mug and moving it here from here, but that mug does not get strained. If I rotate this mug, I'm also changing its position, right? But that does not make the mug strained. So that's the hallmark. So let us talk about this fiber, simple 1D fiber, like a fiber, and then I'm changing its length by pulling it, let us say. So that is the only strain I'm interested about. I'm not interested about its rigid movements. So that means this E is called half of C minus I, that is the Cauchy-Green strain tensor. And then this should, so if I say, if I rotate it, then F would be equal to R. Let's say R is a rotation tensor, rotation matrix basically. So F transpose F would be a R transpose R, because F is a rotation, because you can characterize any rotation by a rotation matrix for deformation gradient. Then that is, you know that R transpose R is equal to I, that is orthogonal. R is an orthogonal matrix. So any rotation matrix is orthogonal. So that has a property like R transpose R equal to I. So in that case, if you replace it here in this first expression, see, ds square minus d capital S square is equal to dx dot F transpose F, that R transpose R minus I, that is 0. So the by rotation, your fiber length cannot change. It's an obvious information, but mathematically that gets interpreted like this, because continuum mechanics is all about writing equations and capturing the physical phenomena nicely, right? So you have to make sure that you're not by mistake understanding a rotation by something like strain. That is another aspect. That is like if you rigidly translate a fiber from one point to another point, then also you're not rotating, you're just translating. Then how do you make sure? Then F is not F transpose F equal to I, but F is itself identity matrix in that case. Because why? Because what is F? D capital X equal to D small x equal to F D capital X. By rigid movements, your D small x and D capital X are same. Okay. Then your F has to be identity. So by construct, F transpose F becomes identity. So F transpose F minus I is 0. So your simple ds square minus d capital S square, the stretch, measure of stretch of a fiber, captures only the strain information of the solid continuum. Okay. So that is why E is a correct strain representation. Any derivative did not be strain. It has certain property. So these are the two properties by which we understand that something is a correct strain measure. Okay, with that we'll go to the next. So when we study continuum mechanics, we should start with the simplest of the problems. What is the simplest of the problems? It is pure extension. You take a bar, you pull the bar or push the bar. Okay. In this setup, how do you characterize that pure extension? Have you ever thought? Suppose a solid, a rubber, if we pull a rubber, you see a thinning effect of the rubber on the other side. You pull it, length is extending, but it cannot change its volume, right? It cannot change because rubber the volume needs to be fixed. So your other dimensions need to shrink in a particular manner. That is why here I am just writing a rule. Let us say small x1 is equal to 1 plus epsilon capital X1. Means initial length of that fiber bar was x1, length of the pen was x1, and I am extending it by epsilon amount. So 1 plus epsilon x1 is my changed length. But since I'm increasing the length in x1 direction, along x2 it should reduce. See 1 minus new epsilon x2. So initial length was x2 in 3D. Now it has changed, it has reduced to new epsilon amount. Okay, that is a valid pure extension rule. Along x3 it is 1 minus epsilon, new epsilon. See, by simple logic, you don't need anything like Poisson's ratio, or these will automatically come. I'm just trying to understand a 3D object, if it gets extended, the other dimension should reduce. Okay. If I write these kinds of small x1 equal to 1 plus epsilon capital X1, small x2 is equal to 1 minus epsilon capital X2, then x3 equal to 1 minus epsilon. Why I wrote new and not only epsilon? When I extended, I wrote 1 plus epsilon, but when I am writing x2 is equal to 1 minus new epsilon, what is this new coming from? Where is this coming from? That comes from how much reduction it should have. So that is something like Poisson's ratio. If it extends certain amount, how much reduction it should have. Anyway, so by this rule, if you want to write the deformation gradient, how do you write that? You differentiate this x1, x2, x3 small with respect to capital X1, capital X2, capital X3. If I do that, so small x, d small x1 by dx, d capital X1, then it becomes 1 plus epsilon. Then if I differentiate x1 with respect to x2, there is no x2 in this first equation, right? So they should become 0. If I differentiate small x1 with respect to capital X3, excuse me, then it becomes 0. Now the second equation, I'm just differentiating x2 with respect to x1. Again, it's 0. I'm differentiating x2 with respect to x2, capital X. Then it becomes 1 minus new epsilon. See, then this deformation gradient is a diagonal matrix. So pure extension means a diagonal deformation gradient. It should not have any off diagonal term. The understanding deformation gradient is a major thing in continuum mechanics, solid or computational mechanics. Because everything, any strain, any stress will require deformation gradients for your information. Now, if this pure extension needs to be volume preserving, as I said, if it gets extended by certain amount, it should be reduced by certain amount. The determinant of f should be 1. That's the requirement. So from there you can say how much new it should be. Okay, that's a different thing. Now let us come to another thing. Second example, a small example. So a simple shear. What is this simple shear about? What does this say? So x1, what I wrote, small x1 equal to capital X1 plus gamma x2. Why? Because in this figure, okay, I think you can see. Yes, in this figure, its x-axis is u1, y-axis is e2. u1 is x, basically the x-axis, the unit vector along x, and then e2 is the unit vector along y. Anyway, so I'm just pulling. I'm just small x1 equal to capital X1 plus gamma capital X2. What does that say? So you see, think about this picture. It's very simple. Let's not go ahead. Now just a small, so it's basically gamma is equal to tan theta. So I'm rotating a box by theta amount. So if I rotate a box by theta amount, tan theta, if I know, then if I go x2 amount, like this, so this from vertical, along vertical dimension, it is gamma x2. So that's the change in my length. That is why I'm writing x1, small x1 equal to x1 plus gamma x2 to explain pure shear. This is very interesting. You see, along y and z, x2, x3, there is nothing, there is no change. So if a body gets pure sheared, its point along x-axis, it changes. It changes along x-axis, but it does not change anything along y and z. So any doubt, anyone? Anyway, so if I do that, then if I try to compute the deformation gradient, how does it look like? See, diagonally it's identity, because there is nothing changed in terms of its stretching, shearing. It's not changed, just its length. So that means it has an off diagonal term gamma. So only one off diagonal term. That is why it is called simple shear. Okay, so that's very basic. I think you all know that. But I'm just trying to rehearse from this angle. You may not have seen, probably, I don't know. So small x1 is equal to capital X1. So initial length, it had a certain length of capital X1 plus gamma capital X2. That's the amount of rotation you give. Okay, so if you do that, then let us come to the next aspect. I'll not take much time, but these are all big issues. So the second thing is T is equal to tau n. What is this T is equal to tau n? That's called Cauchy's theorem. So towards T, small t is traction. Just think this famous problem. The notations are slightly different. I've taken it from somewhere anyway. So the traction on the surface. So what is traction? Traction is force on the surface divided by the area. As area tends to 0, it becomes traction, contact area. So on the surface, how much force you are giving, that's called traction. Now this tau is stress. So that's happening inside the body. So that's quite non-trivial, I would say. This Cauchy did this derivation. T is equal to tau n. N is the normal vector. N is the normal vector. Okay, on this surface. So at any point on the surface, your normal vector is n and traction is t. If you know these two, you can compute, or you know how much stress it should have. So what is stress in a three-dimensional setup? What is stress? Stress is, by definition, is pretty simple: force per unit area. So if you cut a section, compute the force on any plane, you will see how much of stress it is. Now, since it has 3 dimensions, it has all the components. So sigma 3.1 or tau 3.1, tau 3.2, tau 3.3, tau 2.1. What does that mean? Force along, let's say, ith, and then the displacement, or like whatever that along, or you are measuring the area you are measuring along the other axis. So that's why it needs 2 components. The stress is 9 by 9 basically. Sorry, 3 by 3 anyway. So that is the definition of stress. We could derive that, but I thought it's not necessary at this point. When you do Newton's law, force equal to F equal to ma, what do you do that? What do you do? Force and mass and acceleration, right? It needs a balanced law. So force must be balanced. That's why basically force equal to rate of change of momentum, right? Newton's balance. So that's what it is called. You can use linear momentum balance is important. In a continuum setup also, let's say dv dt. What is v? V is velocity. So rho dv, so rate of change of momentum. V is velocity. This capital D is nothing but total derivative. Then equal to divergence of tau, divergence of stress. This you all know, plus sig rho b. B is the body force. For example, self weight, or it can be a magnetic force. It can be any body force. And divergence of tau, that is stress, comes from this Cauchy's formalism. You give a traction force on the surface, and you develop that develops certain stress within the body, right? Within the body, and that's why it is divergence of stress. Now, there is another balance of momentum that is needed. That is balance of angular momentum. Balance of linear momentum we did. That the consequence is the equation of motion that you always solve. Rho dv dt is equal to divergence of tau plus rho b. Now, balance of angular momentum we don't solve for. Why? Because we have already satisfied it. It can be proven. I have not included the proof here that tau is equal to tau transpose in usual setup. Non-classical, non-local mechanics, it does not get satisfied, but usual mechanics, tau is always symmetric. Now, symmetric stress essentially implies that you have already satisfied balance of angular momentum. Okay, so these are the three founding aspects. One is the notion of stress that comes from the Cauchy's theorem, that is traction is equal to stress into unit normal. So traction is how many dimensions? 3 by 1, right? Because it has three components along x-axis, along y-axis, along z-axis. Unit normal, of course, it has 3 dimensions along x, along y, along z. So tau is 3 by 3. So 3 cross 1 is equal to 3 cross 3 into 3 cross 1. So what does it transform? It transforms a surface force into its equivalent volume force in certain way. So this box, it's a representative figure. Stress acts at a point. Stress does not act on a box like that. We talk about stress at a point. Only pictorially to understand, we use these kinds of figures like box figures. Okay, there should not be any confusion about that, I believe. Once we have done that, then comes another aspect. What is that? Frames of reference. Because you may be using solid mechanics for solving a moving car, or a merry-go-round, or a moving ship, or a building, or a bridge that's vibrating, right? So the phenomena, deformation or vibration phenomena of any structure, we civil engineers call everything structure. Okay, we see it from a frame of reference. We have x, y, z, that's the frame of reference. Now, if you change the frame of reference, how does the law change? That is quite important, because if everything changes you should be careful, right? You should what's the rule of shifting from one frame of reference to another frame of reference? Here I've given two frames of reference. One is O star, one is O. Let us say you have a scalar variable that is phi. Let's say it is density. So density should not change by changing your frame of reference, right? Because the material property. So but you're mathematically you're writing an equation. So equation does not know whether it's a density or it's something like displacement or whatever, right? So you should enforce, you should emphasize, you should make your equation understand that this is physical and this is unphysical. So to do that, we have to have this extra measure. This is the next step. That is to make sure that your variables, scalar variables, are following or obeying the rule of frame of reference. That is phi star equal to 5. And if it's a vector, V is a vector, you have a vector at a frame of reference O. Then it should be it transforms into QV in another. So it's a Q is an orthogonal matrix. Cos theta minus sin theta 0, sin theta C minus SSC 1, right? Cos theta minus sin theta 0, sin theta cos theta 0, then 0, 0, 1. Okay. So I'm talking about a two-dimensional problem for our simplicity. So vector V under a changed frame of reference becomes QV. This we know. So these are the rules. So suppose your variable, you have written an equation that does not obey this, then you should understand that you have made a mistake. Mistake where? Mistake in interpreting certain variables correctly. So your notion of stress may be erroneous if it does not satisfy certain property. What is that? So suppose if it's a matrix, for example, stress, T is a matrix, 3 by 3 matrix. If it has to be a valid definition, you just know, you may see there are multiple definitions of stress. For example, Cauchy stress, Payola-Kirchhoff stress, first Payola-Kirchhoff, second Payola-Kirchhoff. You know, there are many different ways of stress definition. But why only few? Why not many other? Because many other definitions may violate certain basic properties. That is why these are very important. So if it's a matrix, then under a changed frame of reference, TQ transpose. These things can be proven very easily. Okay. And this property is called objectivity. If it violates objectivity, then it's an unphysical thing. For example, rho naught. Rho naught is the density of a body before applying any force on it. Okay. Before applying any force on that. Fine. Now, after application of force, you can say maybe these are like you have to so it's rho star J star. J is a Jacobian matrix. You can do it. That's the conservation of mass. Now, if it becomes objective, then rho star J star is equal to rho J. Okay. Since Jacobian is known to be objective, your density must be rho star equal to rho. So this is a very trivial example that I have included here. What is that? That is like saying that density cannot change by changing the frame of reference. Similarly, your traction vector T star has to be equal to QT. And your stress, Cauchy stress, is objective under change of reference in the sense that tau star equal to Q tau Q transpose. And so the last line, the law of balance of angular momentum is frame indifferent. How do you know that? Since you know that tau star transpose equal to Q tau star Q transpose. By doing this thing, you can prove that that tau star transpose equal to tau star. So the angular balance of momentum, angular momentum balance, that is tau transpose tau, is also valid for tau star transpose tau star. Okay, these are the certain proofs, as I have said here. Tau star equal to Q tau Q transpose. There's another thing that is called second Payola-Kirchhoff stress. As I was saying, there are different Kirchhoff stresses. So I thought of including these things. These are the things that you must understand if we are doing in computational mechanics. That is, S is a definition of second Payola-Kirchhoff stress. So there are stress like Cauchy stress, tau, second Payola-Kirchhoff stress. So how? So second Payola-Kirchhoff stress is automatically objective, because S star is equal to S. You can see this derivation: J star F star inverse tau star F star inverse transpose. Okay, and J star is equal to J. If you do this cleverly, you will prove that S star equal to S. So if S is a very easy and reliable variable. So the takeaway message is better to use second Payola-Kirchhoff stress instead of Cauchy stress. Why? Because second Payola-Kirchhoff stress is automatically objective. You don't have to do any transformation. S star is equal to S directly. Whereas the other, like tau star equal to Q tau Q transpose, you have to do all that operation in Cauchy stress, okay, to make that objective. And if you don't make it objective, then you are doing something wrong. So this I'll not go into very much detail of that, but I'll just mention there is something like stress rate. You probably might use this, when you talk about plasticity. Okay, so you must have heard Truesdale stress rate, Jaumann stress rate. There are other stress rates also. Okay, why in hypoelastic material we use the word stress rate? They are the variables that we need. So how do you come up with these variables? Why only few stress rates? Why not one more? Because you have to ensure they are objective. And by doing operations like this, I'm not getting you the detail. If anyone interested, I can discuss later on. So you can prove that certain, you see, by this operation, you come up with some tau box, tau ball, with that automatically gives you an expression. And that becomes your Truesdale stress rate. And Truesdale stress rate is objective in a way that Cauchy stress is objective. So tau ball is equal to Q tau Q transpose. Even stress rates are also objective in this way. Okay. Jaumann stress rate, it is defined like this. But how? Again, in this similar way, if you derive, you get an expression. Very easy. Just definition of S. J F inverse tau F inverse transpose. That's the definition. You don't have to do anything else. Just take time derivative. So J dot time derivative. Then on the second term, J F dot inverse. Then third one is J F inverse tau dot inverse transpose. Like that. Chain rule. By doing that, you just now try to do some jugglery. That is J dot is equal to trace of L. That is velocity gradient. You have to do it nicely, and then you automatically get that expression. So that is how these definitions of different stress rates were brought in. Okay, so I'm not going to the much detail of that, but if you know the Balance law, you have understood how to prove objectivity of certain variables like strain, stress. You know what is frame of reference. That the next thing is constitutive relation, because you now go back to your original set of equations that you can get. Yeah, T is equal to tau n, and then you are getting rho dv dt is equal to divergence of tau plus rho v, right? V is velocity, but your tau is a stress. Still, you don't know how tau is related to V. How is tau related to V? Okay, that is the another important thing. So that is called constitutive relation. To know tau or stress with respect to strain. If you know tau with respect to strain, that is displacement variables, the derivative of displacement, you can solve this equation. Then your problem is closed, but not without knowing the constitutive relationship of a material. So for a material, you must be knowing the constitutive relation, okay, to be able to solve it. So as I was saying, isotropic elasticity is equivalent to doing this operation. Tau FQ, Q is that orthogonal matrix, is equal to tau F. So if your deformation gradient undergoes a certain frame of reference change, your stress should be same. That's equivalent to saying that it is an isotropic material. Why? because deformation gradient derivative information, you are rotating the reference frame, you are still getting the same stress. That can only happen when your material is isotropic. Okay, so you are measuring your stress in certain reference frame, you have changed the reference frame, your stress is still same. That can only happen when your material is isotropic. So same thing. So that is the so Cauchy stress can be written like this, and then second Payola, first Payola stress can be also written. So you see there are Q's coming in. So these things can automatically come. If your deformation gradient undergoes certain rotation, a change of frame of reference, then your Payola Kirchhoff stress looks a different form. And if it gets this specific form, then the material has to be isotropic. That's a mathematical way of understanding whether certain material is isotropic or not. Okay, so then you get these kinds of Rivlin-Eriksson representation, where you are connecting tau with B. What is B? B is some kind of FF transpose, right? So that is how you are connecting your stress with strain. Okay, in a generic way. So sigma is equal to E epsilon falls within this, but you can get nonlinear material, right? Like geosynthetic materials, like rubber materials, like polymers, where you don't get linearity. There you have this generic representation of materials. So beta -1 and beta 1 are experimental parameters, which you find from experiments. If you find that, then you get tau and F, deformation gradient and stress, connect these two. Once you have connected these two, you have known a proper constitutive relation for your problem. Okay. Now this beta -1 and beta 1 are very interesting. People have done experiments and then found that beta -1 is typically negative and beta 1 is typically positive. This is an experiment observation. Once this beta -1 and beta 1 are some numbers, constants, okay, but non-zero constants, then we get Muni-Rivlin material. For example, rubber. And if your beta -1 becomes 0, so you have your tau is equal to -p plus beta 1b. You don't have this beta b minus b inverse term if your beta -1 is 0. That is called neo-Hookean material. Hooke's law, right? Hookean material, like steel, up to linearity, it's a Hook, it follows Hooke's law, right? There are other, rubber does not follow Hooke's law. Then that's the rubber is called Muni-Rivlin type of material. Then neo-Hookean, it may be a plastic type of material. There are different materials which has a different stress-strain relationship. That is found from these two parameters, beta -1 and beta 1, in this Rivlin-Eriksson representation. The most generic way of understanding material property. Okay. Then I'll summarize. Now I'll go, I'll switch off all the maths. Take a simple problem, very simple problem, that is divergence of sigma equal to B. That's the, what is that? Linear momentum balance equation. Divergence of sigma is equal to B. That is linear momentum balance. And since sigma is equal to, sigma is symmetric, you have already taken care of the angular momentum balance equation. And your density is constant. So you have already accounted for mass balance. There are three balance laws that you must solve. One is mass balance, second is linear momentum balance, third is angular momentum balance. And these three for conservative systems. If the systems become non-conservative, then you have more equations. That is energy balance, okay, temperature balance. These are different things. We're not talking about that. We're talking about conservative problems where there is no dissipation, nothing, no friction, nothing. Then you have three equations. Mass balance accounted for because you assume that density is constant throughout the evolution of the problem. then you assume that your sigma is equal to is symmetric, so you already have accounted for momentum balance. So only one equation you have to solve for, and that is what you solve. Yes, I think somebody has a raised hand. Shall I continue or? Hello?
Sir, please continue.
Okay, thank you. So this is a partial differential equation because it has derivative. So suppose you have du dx equal to 1. The differential equation, if you want to solve, you need boundary conditions to solve for. You cannot solve any differential equation without any boundary condition. And those boundary conditions in this context are called Dirichlet boundary condition and Neumann boundary condition. So suppose you have this pen, you are pulling this pen by certain force. If you don't hold this here, this pen will go with you. So it will not have any deformation. If even you apply some force. Okay, so you must apply some boundary condition holding the pen. Then if you apply force, then it can deform by certain amount. That is what u is equal to u0 on some domain. You see, this is a domain, this blue one is a domain, where the left part, blue boundary is, let us say, it's SU, that is displacement boundary condition or Dirichlet boundary condition, and red portion is where you apply some traction. So in this pen, blue boundary is the place where we are holding this pen, and red one is where we are pulling this pen. But you cannot pull a pen where you are holding it, right? You cannot pull where you are holding it. It will not move. That is why Dirichlet and Neumann boundary conditions, they don't overlap each other. They are different. They don't have overlaps. So that is why I've drawn it separately. ST and SU, they are disjoint usually. Okay. Why? Because you cannot simply pull somewhere where you are holding it. It will not going to move anywhere. So anyway, with this proper boundary conditions in terms of traction and displacement, then you need a proper constitutive relationship. In this case, I have taken a very simple one, which we all take. Sigma is equal to d epsilon. Sigma is equal to d epsilon, that is sigma is equal to 2 mu epsilon plus lambda, trace of epsilon, something that we all know. 2 mu epsilon plus lambda divergence of u. Okay. Then mu and lambda are Lamé constants, which are related to Young's modulus and Poisson's ratio by these laws, like mu is equal to E by 2 1 plus nu, and lambda is equal to E nu by 2 1 plus nu into 1 minus 2 nu. This all we know. The problem is now well posed. Your domain is omega, blue domain, where you want to solve. It may be aeroplane, it may be a building, it may be a simple pen. Somewhere you are holding it and somewhere you are pulling it. Okay, like that. It has to deform. Then the problem is your rule is divergence of sigma is equal to b, and then your so what we have learned here, first thing is the Dirichlet boundary condition or displacement boundary condition and Neumann boundary condition or natural boundary condition, they cannot overlap with each other. They are disjoint. Okay. Then we come to directly FE discretization. So we discretize this domain by small meshes. Here we are talking about some finite elements. So we need a background, but how much time we have? I think, we are almost done, right? Okay, so I'll quickly just, so we discretize a body with regular shapes. It can be boxes, it can be pyramids. In 2D, it can be rectangles, okay? where we can numerically solve the problem easily, and then we assemble the small pieces and make a big building. That's the finite element. About finite element, your element is finite domain. It's not very small, it's not very large, so it has a domain. That's finite element method. So we discretize that field variable, that is u, displacement, as ni ui. N is a shape function, u is a displacement, but this ui are displacements only at the nodes of the finite element, and with that you are approximating the displacement at any point within the domain. Okay, so your ux is a field variable, that is continuum variable. Since you cannot solve the problem exactly for any engineering problem, first thing we did was finite difference. Long back we did. What was that? That was du dx equal to u2 minus u1 by delta x. So you are approximating derivative by two nodal values, u2 minus u1. But that turned out not to be sufficiently correct for many of the problems. So we tried to do another approximation, that is, you take a small portion of the whole body and then approximate ux as summation of ni ui. So on that small portion, the domain boundaries like nodes. So in case of box, it is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So IENE number of nodes for an element is 8 in that case. So you are different. Then if you once you have discretized this ni's are functions of spaces, that is x. Okay, and u's are functions of time in case of dynamic problem. Okay, then you just put this discretization back to this equation, divergence of sigma equal to b. Fine. And then you solve it weakly. What does that weak solution mean? You multiply with this shape function on the left hand side in addition, and then integrate over the entire domain of that element. Then you get back equations like this. Okay, so n is shape functions matrix, and then d is the displacement, nodal displacement vector. I'm just quickly going through that. If you have any question, you can ask. Okay, then we solve that problem. How? Oh my God, where did it go? Yeah. To make it more explicit, what I've done, I've taken an even simpler problem. That is, dou sigma xs by dou x plus dou sigma xy by dou y equal to 0. Dou sigma xy by dou x plus dou sigma yy by dou y equal to 0. Simple equation, 2D equation. Then the constitutive relationship is sigma xs, sigma yy, sigma xy equal to some matrix, that is constant matrix, into epsilon xx, epsilon yy, and gamma xy, that is strain. So stress equal to some matrix into strain, linear Hooke's type of constitutive relationship. Then strains are related as, what is epsilon xx? That is dou ux by dou x. Epsilon yy is dou uy by dou y. If you arrange it in a matrix form, it looks like that. Dou x 0, 0 dou y. Then last one is dou ux dou y plus dou uy dou x. So that is how the strains are. Okay. Then we write this b is what? B is that dou x, that operator, differential operator. That is dou x 0, 0 dou y. So that is b is that differential operator into sigma. Simple. That equation that we have just written can be written in this matrix form, that is b transpose sigma equal to 0. And sigma is equal to d epsilon. D is that constant matrix that we just have seen. Epsilon is a strain vector that we just have seen. Then the problem remains to be discretizing u as ni ui. Okay, and uy as ni uy. Okay. Then we just put these things back and we get a force vector, we get a mass stiffness matrix like this. I'm just quickly doing this, and then we have element stiffness metric, that is K is equal to integral B transpose dB, and P is equal to this Lxyz. We have written the differential operator of the shape functions. So we are transforming the differential operator on the shape functions instead of the field variables continuum in this separation of variable mode, that is u is equal to ni ui, where ni are known polynomial functions and u's are nodal variables. Okay, so that is why I end. I think I have finished it well before, but I have done this purposefully just to make sure that we have ample time to discuss if we want, because it's a very heavy thing, I think. So probably Dr. Rajan can, if anyone has any question.
Yes, sir. Thank you, sir. Now we will ask the participant to have any question. So the participant can put their question in the chat box of Professor Saikar Sarkar.
Yes.
For any query or any question regarding this topic.
Yes. I think I'll end in that case if there is no question. So was it fine, or should I make it more elaborate?
Yes, yes. So we will wait for any question.
I prepared it for 1 hour. I think I finished it in 1 hour.
So is there any question from the audience side?
Then maybe.
Yes, I think there is one question.
Okay.
Can I raise the question? It is by Lukesh Parida.
Okay, thank you. Yeah,
he is asking that, sir, please explain a bit of non-linearity. Sir, please explain a bit if non-linearity come into the picture.
Yes, exactly. So that is what I was referring to. I'll go back to my slides. Yes. See, tau is equal to minus P, that is pressure. B inverse B minus 1 B inverse. This B is a strain, right? F transpose. B is FF transpose, the deformation gradient. Now the strain, so this stress versus strain relationship is non-linear. That is why we have done all the thing to account for non-linearity. We are essentially solving non-linear problems because stress and relationship is essentially non-linear here. It's not linear. So linearity comes as a strict subset. If there is no linearity, then B minus 1 is 0 beta. So it is a linear problem. In that case also, see, FF transpose, B is what? B is FF transpose, right? So if you now, what is B, what is F? F is I plus grad of U, right? So I plus grad of U into I plus grad of U, FF transpose, isn't it? If you now expand this, what do you get? I plus grad U transpose plus grad U into grad U. You see, grad U means du dx, right? So I plus du dx, that's linear part. You have du dx into du dx type of term. By construct, B is a nonlinear strain. So whole thing is nonlinear. Okay.
So is there any question from the audience? We will wait if anyone can put the question.
Yes. So what do you think? Was it kind of clear, or I was going a bit fast, or was any feedback? That is also fine.
Okay. One more question has appeared in the chat box, sir. Can you read the question? Professor, second. I think Satish Kumar AS. Professor Satish Kumar AS is asking one question.
Can you read it?
Shall I read the question?
I'm not able, yes, please, because I cannot. I'm not able to open that chat box.
Yes, he's asking that, sir, is the moment distribution method is used in also in situ also, or only in theory application only?
Moment distribution type of approaches are kind of getting obsolete slowly, I believe, because we are now having some stat pro, any finite element packages, right? So there you can solve these equations by matrix methods. Matrix methods means that you have truss, frame, element matrices, you assemble and then solve easily. Because the moment distribution methods came because we needed to solve equations where we did not have huge computers. So slowly, still used, but I think more and more we are going for this matrix method and then find proper finite element based approaches. You have softwares, right? You can easily solve very complicated problems. Okay, that's my view. I don't know about others.
One more question is there. Professor Param Gajbi is asking, in 3D elastic problem, constitutive relationship for isotropic material are same as composite material.
I mean, is it same as? No, composite materials. What is it? Composite means it's a composite of two materials, three materials, right? Each material will have a different constitutive law. For example, ceramic polymer composite. Ceramic has its own constitutive relation. Polymer has its own constitutive relation. Both you use together. Okay, then you write the equations properly. That's a different. But yeah, but in another case, why do you use something like concrete? But you have many other materials like cement, sand, then you have what is that called? Aggregates. Each one is a different material, right? But we don't use very different constitutive relations for writing. So cement is kind of a homogenized uniform constitutive relation for use. That's effect whose effect comes from all the materials. Yes, so that's how cement, like concrete's constitutive relation is different from cement's constitutive relation because it accounts for effect from all other materials. Okay. Yes. So what is the effect? I can see the chat now. So what is the effect of non-associated flow rule on hearing capacity of a strip footing? What is the flow rule of on the bearing? No. See, that's a different point of view, and that's a different question altogether. This bearing capacity of a soil. That's an experiment. You go to this field and you measure. Okay, that's a different point of view. That we are interested mostly about the deformation of footing, for example, whose effect comes from soil. Okay, so let's not try to bring in everything together because this soil is a very different thing altogether. Okay, then traction tensor of rank 1 and stress is a tensor of rank 2. It has 9 components for what is the question? I'm not probably getting it. Traction, no. Yeah, rank is fine, but traction is a vector of 3 dimension. So traction is a 3-dimensional vector and stress is a 3 by 3 vector. Okay, 3 by 3 matrix, sorry. So I don't know, for a point in pure shear, I'm not able to get the question properly. What is RTR? I don't know. Properly, if you could understand, then I could probably try to answer that. Anyway, for FEM, is there any rule for deciding the number of? No, that's a very good question actually in the context. Yes. See, there are two things in FEM. One is H, one is P. What is H? H is the length scale of an element. That's why it is called HP refinement. Either you can increase the polynomial order of finite element mesh, or you can use more and more small small elements. So if you increase the polynomial, your accuracy goes high. If you increase the number of nodes, your accuracy goes high. So both way you can increase the accuracy, and there is no end to your refinement. You can go to infinitely more and more nodes. right, to increase the accuracy. But the question is, do you go for that? Such so many? No, because final goal for FEM is to solve problems with as less computation as possible. So that is why we do test something like convergence study. So you take a less number of nodes and lower order polynomials and then solve problem. Then you go to a go to a slightly defined mesh, then again see a solution. Then you plot them, or you see the error, how the error is reducing. If you see your error curve is kind of reaching a plateau as you increase the number of mesh, a number of nodes. Okay, then you kind of assume, okay, fine, I am now I have now attained the convergence, so I don't need to go for any finer. So you cannot just in one go, you cannot say this is my correct solution. If you had taken n number of nodes to solve your problem, you must take more, 2n for example, or n plus 50, whatever. Then see your solution whether they are kind of approaching a plateau, approaching a convergence. Once it approaches, then you assume this is the correct solution. Okay, that's a very good question. What is the effect of non-associated flow rule on BI? No, that's not a related question, I believe. Then in the balanced law slide, the mass is considered in space, that is without with any axis y. What is the question? Mass is considered in the space without coinciding with any. No. That's just demonstrate. I mean, I have just drawn some axis. Okay, so it's like some axis. You are drawing something. You are putting something here. So there is no. I don't see any problem with that. For APM, is there any rule for deciding number of nodes? Yeah. What is the effect of non-associated? No. I think these are the questions. Yeah, somebody liked it, interesting and in detail. Yeah, I tried to make it in detail because I think if I go on putting slides and some results, nothing gets transmitted. Better to understand it thoroughly. And that's my way of seeing the problem. In the last slide, to the elasticity rotational metrics for rotational metrics, yeah, that's again I think I can it's a good one. So any deformation gradient tensor has two different parts. One is stretch, one is rotation. So F can be written as U into R. U is the stretch matrix, R is the rotational matrix. That is called polar decomposition. Okay, that's another, you can read about this. So any deformation gradient can be split into two parts to understand how much is contributing to rotating the element, how much is contributing to stretch. This is very much interesting when it comes to plasticity, because in plasticity these rotations are like these rotations dominate in many cases. Flow plasticity is a flow type of thing, right? So there you can see many interesting aspects of in that. Beam how plate element, how, yeah, of course, any large deformation problems, you cannot solve such things analytically. You need a discretization numerical scheme, and FEM is one of the numerical schemes, which is probably the best one, one may argue. Okay, so you solve a large deformation problems in an iterative manner mostly. So you take small load steps delta U and then solve it again. Then you take a new load. So you go by converging iteration. Then you solve that I have discussed can account for. That's why you get the stress measures like Buni-Rivlin, Neo-Hookean. These are all different stress strain relationships which can account for. Because see, rubber can deform very large amount. That does not stop us from solving that problem. This with the notations used in the earlier slide of continuum mechanics. Yeah, see, there are some, see, that may happen. Tau is same as sigma. That you should pardon me. I have taken this equation maybe from a book or some paper, something, there. So yeah, I should mention. Yeah, please. Sigma is nothing but stress. Okay, but yeah, that's a good point. FEM for any other method used for 3D elasticity problem? Yes, of course, any 3D elasticity problem can be solved using FEM. Then circular shaft with a torque, rotation matrix. I don't understand this question. It's not a question, maybe it's a comment. Yeah, of course.
Okay,
Discuss about
so shall we
governing.
conclude now?
Yes, I think there are many
Yes.
questions we can discuss. If
There
anyone is
may
interested.
make many questions now.
Yes.
Yes, yes.
Yes. Okay.
Because within short period we cannot answer
Cover
to each and every
everything.
questions.
Yeah. Yes. Yes.
But
yes.
you have addressed many questions.
Thank you. I tried.
Okay. So I will conclude now. Okay.
Okay.
So we will come to the end of this session.
Okay.
So I am very much thankful to Professor Saikar Sarkar for accepting our invitation to give the expert lecture for this FDP. And sir has given a very nice session. And the problem of the solid mechanics and continuum mechanics has been well explained by Professor Saikar Sarkar. And he has given the very innovative explanation for the theory of elasticity and plasticity, of course, because we learned this subject of solid mechanics and theory of elasticity and plasticity during our B and M.Tech. Now he gave us some refreshment over this topic. Of course, there is the application of this formulation for the analysis and design purpose. And our participants enjoyed your session a lot as they understood the formulation of mathematics. There are so many questions to you.
Yes,
so we are very happy to see you, and we are very happy that you have given your valuable time to us for our FDP. So on behalf of our college, that is on behalf of the Government College of Engineering Karad, the Department of Civil Engineering, and Department of Applied Mechanics, Government College of Engineering Nagpur, we are thankful to you for your precious, for giving your precious time. So thank you very much, Professor Saikar Sarkar.
Thank you, Dr. Rajan,
Yes,
and
yes.
thank you all for your patience.
Welcome, sir. Welcome.
Thank you.
So shall we end this
Yes.
session now?
Okay, then bye.
Oh, okay, sir. Thank you.
Yes, sir. Thank you, sir.
Shall we end?
Yes, sir. Yes, sir.
Tomorrow we will start the session at the 10 a.m. in the morning.
Okay, sir.